You know, it's funny. When you pick up a physical book, your brain is doing something incredibly complex without you even really realizing it.
Oh, absolutely. It's completely subconscious.
Right? You look at the cover, you see some like large stylized text, and you just instantly know, okay, that's the title.
You don't even have to think about it.
Exactly. And you see the smaller text under it, and you're like, that's the author.
Hmm.
You don't read the title and mistakenly assume it's, I don't know, the opening sentence of the story.
Yeah, you inherently understand the structure of the physical object you're holding.
You subconsciously separate the information about the book from the actual contents inside the book. But when you hand a standard plain text file to a computer,
It's completely blind to those visual cues.
entirely blind, you just see this massive, flat, unyielding wall of letters.
Because to a machine, without, a set of explained instructions, the letter A in the author's name is fundamentally indistinguishable from the letter A in the middle of chapter 4.
It's just data.
Right. It's all just a continuous, linear stream of data. It's completely devoid of context or hierarchy. I mean, the computer doesn't know what a cover is. It doesn't know what a title page is.
Okay, let's unpack this, because bridging that exact gap, teaching a computer to see structure where there literally appears to be none, is the specific challenge we're exploring today.
And it's a great challenge.
It really is. So whether you're a seasoned software developer looking to, brush up on functional programming concepts in Haskell, or you're just a curious learner fascinated by the invisible mechanics of how machines read, this deep dive is custom tailored for you.
We're basically getting into the foundational mechanics of software parsing.
Right. Specifically, how to build a tool that can scan a document, intelligently identify the metadata, the structured data about the file, and cleanly separate it from the actual narrative body of the text.
We're essentially talking about writing a set of rules that gives the computer the ability to categorize information dynamically.
Dynamically, right.
Yeah, we needed to transition from treating text as a monolithic block to treating it as, well, a collection of distinct categorized fields.
And our source material gives us this really specific real-world programming scenario to anchor the whole discussion.
It's a great example to work with.
So we're working with a plain text file of a Chinese novel. And at the very top of this file, there's a dedicated block of text.
Right at the top.
Yeah. It's enclosed by 3 dashes on the top line and 3 dashes on the bottom line. And inside those dashes, we have 2 critical lines of info.
The metadata.
Exactly. The first line translates to book title, tale of Qingyunsec cultivation. And the line right below it translates to author, anonymous.
And then the story starts after that.
Right. After the closing dashes, the actual narrative begins with chapter 1, incomplete scroll in the youth, and then the first paragraph.
What's fascinating here is that 3-dash convention. It's actually quite common. Oh, yeah. If you've ever worked with, markdown files or static site generators, you definitely recognize that as YAML front matter.
Oh, right, YAML.
Yeah, it's this very clean, human-readable format that's basically designed to embed structured key-value pairs directly inside an otherwise plain text document.
It is beautifully human-readable.
Mm-hmm.
But the current implementation of the parser reading this file perfectly illustrates the problem with what we might call dumb text.
Right.
Because right now, the program looking at this novel processes everything as if it holds the exact same narrative weight.
It just doesn't know any better.
It treats those crucial structured metadata lines at the top as just mere story paragraphs.
Yeah, the current system completely misses the structural boundary that those 3 dashes are, trying to communicate.
When the parser runs right now, it generates an output log that looks kind of ridiculous. It says paragraph dash dash dash. The paragraph book title, Tale of Qingyunsec Cultivation. Then paragraph author anonymous. Then another paragraph dash dash dash.
And only after churning through all that metadata noise.
Right. Only then does it finally register chapter 1. It's completely blind to the fact that those first few lines serve a fundamentally different purpose than the rest of the text.
It's treating everything exactly the same.
To give you an analogy, it's kind of like handing a complex multi-course menu to someone who has literally never been to a restaurant before.
Okay, I like that.
Right. They look at the menu, and they don't realize that the word appetizers, printed in bold at the top, is a category heading.
Oh, I think it's food.
They just assume appetizers is a specific dish they're supposed to order. Our parser basically thinks the book's title is just a very confusing, poorly written first sentence of the story.
That visualizes the friction perfectly. And, the core issue here isn't just an aesthetic annoyance where the computer logs things incorrectly.
No, not at all.
It actually represents a hard functional roadblock for whatever application needs to use this text file later.
Well, let's follow that thread for a second. Say I'm building an app, and honestly, I don't care if the computer thinks the title is a paragraph.
Okay.
I can still open the text file and read it myself, right? So why does the machine's lack of structural awareness actually matter in a practical sense?
Well, consider the end goal of the developer in our source material. The
Mhm.
whole objective is to use this text file to automatically generate a fully formatted digital ebook.
Ah, an ebook.
Right, an ebook generator relies entirely on discrete variables to plug into its visual templates. It needs to know, absolutely unequivocally, what the title is so it can render it in a huge font on the digital cover.
So it can't just guess.
Exactly. It needs to know the exact author's name to populate the digital table of contents and the file's internal metadata tags. A generator can't simply, guess which paragraph happens to contain the title.
It needs the data handed to it in isolated named variables.
Exactly. The parser must be capable of recognizing explicit boundaries to transition its internal logic from story mode into information mode. Without that ability, automation just becomes impossible.
Which brings us to the Haskell solution presented in the sources. And this really requires us to shift our perspective on how we solve programming problems in general.
Yeah, definitely. Haskell forces you to think differently.
Because we're working in Haskell, which is a statically, strictly typed programming language, before we even begin to write the logic that searches for those three dashes.
The source material dictates that we have to change the underlying vocabulary of the program itself.
Yes. We have to literally define our reality.
We have to give the compiler the conceptual blueprint of what metadata actually is before we can ever instruct the parser to go locate it.
So the first major architectural change involves creating a brand new data type from scratch.
A new blueprint.
Right. The code defines a structure literally called metadata. And inside this new blueprint, it dictates that there must be two distinct text fields.
One for the title, one for the author.
Explicitly named title and author. We're basically constructing the conceptual boxes that the parser will eventually use to store the extracted information.
We're defining the exact shape and requirements of the data we expect the text file to eventually yield.
But it goes further than just, creating a new box.
Yeah.
Previously, the overarching data type that represented the entire document, which is simply called content, only understood two concepts.
Let me guess. Chapters and paragraphs.
Exactly. A piece of content could either be chapter text or it could be paragraph text. That was the parser's entire worldview.
Very limited.
Super limited.
Yeah.
So to fix the issue, the developer updates this content type by adding a third completely new option. Now, a piece of content can be chapter text, paragraph text, or metadata.
By doing that, they're elevating the new metadata structure, injecting it right into the foundational hierarchy of the document's permitted contents.
Now, I kind of have to stop and push back on this approach for a second. My instinct, especially coming from more flexible, dynamically typed languages like Python or JavaScript, is to just solve the problem directly.
You want to take the shortcut?
Well, yeah. If I know the text file has a line that says book title : why do I need to spend time re-architecting the foundational data structures of my entire program?
It feels like overkill.
It does. Why can't I just write a quick regular expression or a script that says, scan down the page, and if you see the phrase book title : just grab the rest of the text on that line and throw it into a variable? Why undergo all this heavy, upfront architectural lifting?
That is a very, very common reaction. And it really highlights the philosophical divide between dynamic scripting and functional, strictly typed languages like Haskell.
Okay, lay it on me.
The quick script approach you describe, using a regex to just grab what you need on the fly, is entirely focused on the action of searching.
Right.
But it completely ignores the guarantee of what you found.
How so?
Yeah.
I mean, if my script finds the text, hasn't it basically done its job?
Let's examine the failure states of a quick search script. When you rely entirely on an on-the-fly search command, you are basically hoping your search pattern never encounters an edge case.
Oh, I see where this is going.
What if a character in the novel is an author, and Chapter 4 begins with the sentence, author : a title he wore proudly?
Oh, wow. Yeah, a naive script scanning for the string author : might accidentally hook onto that sentence deep in the story.
Exactly. It would extract the rest of the paragraph and silently overwrite the actual metadata variable.
It would confidently inject a piece of the narrative right into the ebook's author tag, and the program wouldn't even realize it made a mistake.
Because the program lacks contextual awareness. In Haskell, by defining these types up front, you're doing something much deeper than just creating variables. You're turning the compiler into a strict proof checker.
That's a great way to put it.
By forcing the data structures to acknowledge that a specific isolated concept called metadata exists and that a document is allowed to contain it, you establish an unbreakable contract. You make it mathematically impossible for the program to accidentally pass a regular story paragraph into a function that specifically requires a metadata object. The program simply will not compile. It forces you to handle the data structurally rather than just textually.
It's the difference between hoping the file is formatted correctly and designing a system that just flat out refuses to operate if it can't guarantee the structure.
The types act as an architectural safeguard.
Okay, so we've established this strict blueprint. The program now has the vocabulary to understand metadata.
Yes.
Here's where it gets really interesting. Now it's time to build the actual machine that reads the text and extracts it.
We need to implement the parser itself.
Right. And in the code, this new parser block is named pipe metadata. And it's constructed using a library called Megaparsec, which is this highly regarded parser combinator library in the Haskell ecosystem.
Megaparsec is incredibly powerful.
And watching how a parser combinator works is honestly fascinating. It's not reading the whole document at once. Instead, imagine like a tiny, highly trained cursor sitting at the very first character of the text file.
Okay, I'm picturing it.
The parser dictates exactly how that cursor moves and what it consumes.
It's a process of meticulously moving forward, character by character, following a really explicit sequence of expectations.
So let's walk through that sequence.
Yeah.
Step 1. The parser instructs our imaginary cursor to look at the very beginning of the document and check for the exact string of 3 dashes, followed by a space.
Right.
If the cursor sees those specific characters, it consumes them, effectively moving past them, confirming it's on the right track.
It eats the dashes.
Exactly. Step 2, the cursor now looks for the specific characters that represent book title :
It's searching for the precise label that precedes the target data.
Yep. And once the cursor consumes that label, it's positioned right at the start of the actual title. So to extract it, the comp uses a function called take_while_1p.
Take while 1p.
This function is so elegant. It essentially tells the parser, keep moving the cursor forward and grab every single character you encounter under one condition. The character must not be a new line.
So it just sweeps rapidly across the rest of the line.
Right, scooping up the characters of the book's title. And the absolute millisecond it hits that invisible new line character, the character that tells a text editor to drop to the next line, the cursor stops dead.
It isolates the data bound by the label on the left and the physical end of the line on the right.
It neatly bundles all those scooped up characters and saves them into our tightly defined variable called book title.
Beautiful.
Then the cursor drops to the next line and repeats the whole choreography. It consumes the characters for author : deploys take_while_1p again to sweep up the author's name until it hits the next new line, and saves that string into the author name variable.
And then it just needs to finish up.
Finally, it looks for the closing set of 3 dashes. Having successfully navigated that entire obstacle course, it takes book title and author name, places them into our rigid metadata type structure, and returns the finished object.
If we connect this to the bigger picture, what we're observing here is the absolute essence of pattern matching and data extraction.
Right.
Parsing with a tool like Megaparsec isn't just about reading. It involves making incredibly precise, character-level decisions about what information to capture, and maybe equally importantly, what information to throw away.
Well, let's dig into that throwing away aspect, because the code imports a very specific function called string from Megaparsec's character library to accurately identify the dashes and the labels.
But it wraps those string searches in another function.
Yes, a function called void.
The void function is totally crucial for cleaning up the data stream.
Yeah.
Well, when you wrap a parser in void, you're giving it a very specific command. You're basically saying, I need you to verify that this exact pattern of characters exists here, but once you've confirmed its presence and consumed it, discard it. Do not return it to me.
Oh, wow. So it verifies the 3 dashes are there, but refuses to save them.
Exactly.
It verifies the words book title, colon are there, but essentially throws them in the trash. It aggressively strips away all the formatting, the labels, the spaces, and the new lines.
It gets rid of all the clutter.
By the time the metadata object is actually built, the only things left are the pure, unadulterated strings of the title and the author. It's extracting the pure signal from the formatting noise.
Because the dashes are just scaffolding built for the human eye, right? The computer doesn't need them taking up memory in the final ebook data.
It distills the text down to its purely structural essence. The parser uses the human-readable conventions strictly as, like, a navigation map, and then just discards the map the moment it reaches the destination.
It's a very clean way to operate.
It is. This parser is a fantastic, precise machine. But anytime you build a machine that expects a very specific input, you kind of create a potential trap.
Right. What if things don't go according to plan?
Exactly. What happens if we feed our newly updated parser a text file that does not have any metadata at the top?
A very real possibility.
Right. What if we handed a raw, unformatted draft that just starts immediately with Chapter 1? We need the system to be resilient. A robust application can't just catastrophically crash because a writer forgot to include a title page.
Handling the absence of data gracefully is a fundamental tenet of robust software design. If a parser cannot fail safely, it's incredibly brittle.
So to solve this, the source material focuses on the logic of the overarching document parser, the function that manages the entire file, which they call pdocument.
And how does pdocument handle it?
To handle the uncertainty of whether metadata exists or not, they introduce two really powerful concepts into the sequence: optional and try. The code establishes a variable called maybe_meta. To populate this variable, it instructs the engine to run our meticulous metadata parser, but it wraps that execution entirely inside the optional and try commands.
Those two commands completely alter the parser's operational parameters regarding failure.
Let's break down the mechanics of how they actually alter those parameters. Let's start with what happens to a parser if these commands are missing entirely.
Right. Without those commands, the sequence is totally rigid. If the main document parser expects the file to start with the metadata block, it immediately looks for those 3 dashes.
And if they aren't there?
If it encounters the letter C for Chapter 1 instead, it registers a critical mismatch between its expectation and the reality of the file. It instantly throws a fatal error, and the entire program terminates before reading a single word of the story.
It fails completely.
It fails completely, yeah.
Because it treats the blueprint as a mandatory law rather than just a conditional possibility. But when we wrap the metadata parser in the optional command, we fundamentally change the rules of engagement. We're telling the parser engine, attempt to find the metadata. If you find it, extract it and give it to me. But if you do not find it, that's a perfectly acceptable outcome.
Do not panic.
Right. Do not throw an error. Do not panic. Just return a specialized value called nothing and calmly move on to the next step.
It transforms the metadata block from a strict prerequisite into a graceful conditional. But optional alone actually isn't quite enough for a text file.
Why not?
That's where the try command becomes vital.
Right, because parsing isn't always a simple binary success or failure on the very first character. What happens if the text file starts with 3 dashes, but it's not a metadata block?
A classic edge case.
Yeah. What if it's just like a stylized scene break that the author decided to put at the very beginning of the manuscript?
That scenario is basically a parser's nightmare. The parser sees the 3 dashes, assumes it's looking at metadata, and happily consumes them. But when it moves to the next line, expecting to find book title : it finds a regular narrative sentence instead. The pattern is completely broken.
And because it already consumed the dashes, you can't just pretend they weren't there. It's stuck halfway down a dead-end path.
Exactly. Unless it's wrapped in try. The try command enables a mechanism known as backtracking. When you wrap a parser in try, you're essentially instructing the program to create a temporary save state in its memory.
Like a checkpoint.
Right. It takes a snapshot of the cursor's exact position before it attempts the parse. If the parser consumes the dashes, moves forward, and then fails because the title label is missing, the try command intercepts the failure.
It catches it.
It tells the engine, stop, do not throw an error. Instead, rewind the cursor back to the exact save state we created, restore the consumed characters to the unread stream, and pretend this attempt never happened.
It's literally a video game save point for the parser's position in the text.
That's a perfect way to describe it.
It allows the machine to venture down a specific logical path, realize it made a mistake, and then flawlessly reverse time to try an alternative route without corrupting the data stream. That mechanism is what makes parser combinators so incredibly resilient.
The combination of optional and try ensures that the parser can handle basically any variation of the document perfectly.
And the final logic of P's document brings it all together based on those specific outcomes.
Right.
If the optional parser succeeds, it takes the fully populated metadata object and elegantly attaches it to the overarching document structure, appending it right to the main body of the text.
And if it fails,
If the parser utilizes that failed state and ultimately returns nothing, the program smoothly bypasses the metadata logic entirely. It just proceeds directly to reading the narrative, applying its standard rules for chapters and paragraphs.
the output log really reflects this architectural victory.
So what does this all mean? When the developer runs the print function on the newly parsed document, it no longer spits out a confusing list of generic paragraphs. Instead, the console clearly and distinctly reads metadata, followed by the isolated label for book title and the pure string of the title, followed by the author, and only then does it output the chapter data.
It's beautiful.
We've taken a raw, flat, visually chaotic stream of text and mapped it into a mathematically sound, structurally flawless data hierarchy.
We have successfully engineered context.
We really have. From the initial decision to define a strict typed blueprint, through the precise cursor movements of Megaparsec extracting the signal from the noise, to the resilient save-state logic of backtracking, we built a system that translates human formatting into machine intelligence.
It is a remarkable demonstration of how software imposes order on the unstructured artifacts of human communication. However, as we conclude this exploration, the very success of this parser forces us to consider a broader implication.
Ooh, I'm intrigued. Where does this lead us?
Well, this raises an important question. Throughout this entire discussion, our ultimate goal was basically building a wall, right?
Yeah, separation.
We engineered a strict programmatic barrier separating the metadata, the information about the story, from the content, the narrative itself.
Right.
And for the specific utility of an ebook generator, that rigid separation is mathematically required. But as you navigate the increasingly complex digital documents and interactive media in your own life, consider how often those boundaries are actually clear-cut. Where exactly does the line between the data about the story and the story itself begin to blur?
That is a profound question.
Yeah.
We treat them as completely binary in code, but art rarely is.
Exactly. Consider a novel like House of Leaves, where the structural formatting, the footnotes, and the architectural layout of the text are inextricably linked to the psychological horror of the narrative itself.
Oh, that's a great example. The layout, IS the story.
Right. Or think about a modern digital article, where the interactive tags and the visual scaffolding actually dictate how you experience the argument. If our underlying digital infrastructure relies on parsers built to ruthlessly isolate the information from the art, what subtle human context might be permanently lost when we force fluid writing into rigid computational boxes?
Wow.
When the machine eagerly throws away the scaffolding, does it occasionally throw away a piece of the text's soul?
That is a phenomenal concept to reflect on. We can teach a machine the mechanics of parsing the menu flawlessly, but that definitely doesn't mean it comprehends the meal we're actually trying to serve.
Perfectly said.
Well, thank you so much for joining us on this deep dive. We will see you next time.